All right, let's just jump right in. For, centuries, we've had this toolkit of simple shapes, lines, circles, squares, that we've used to try and describe the world. But if you actually stop and look around, you realize nature almost never uses them. The real world is rough, it's messy, it's kind of jagged and infinitely complex. So how do we even begin to describe that? Well, it turns out we needed a whole new kind of geometry.
And to get our heads around this, let's start with what sounds like a really, really simple question. How long is the coastline of Great Britain? You'd think you could just look that up, right? Get a single number and be done with it? But as you're about to see, the answer is way stranger than you could ever imagine.
So, let's say we try to measure it. We pull up a map and we take out a big, kind of clunky ruler, one that's 100 kilometers long. We lay it out point to point along the general shape of the island. And when we do that, we get an answer of about 2,800 kilometers. Okay, seems reasonable enough. A nice, solid number.
But watch what happens when we get a better ruler. Let's swap that one out for a much smaller 1-kilometer ruler. Now we can get into all the little nooks and crannies, all the little bays and inlets. And when we do that, the length suddenly balloons to over 8,000 kilometers. That is not a small change. It's almost 3 times longer. What is going on?
This is the absolute heart of the mystery. The closer you look, the more detail you find, and the longer the coastline seems to get. And this isn't just some measurement error. It's a real, fundamental property of the shape itself. It has a name, the coastline paradox. And it was first really dug into back in the 1950s by a guy named Louis Richardson.
What Richardson figured out was pretty revolutionary. He realized that for jagged, complex shapes like a coastline, length isn't some fixed, concrete property. The problem wasn't the coastline. The problem was our ruler and our entire idea of what length even is.
So, what does that actually mean? It means length isn't baked into the object. It's a relationship between the object and the tool you're using to measure it. This one idea basically broke classical geometry. It showed us we needed a brand new language, a new math, to describe the inherent roughness of the world around us.
So if our old rulers are broken, what's the solution? Well, it lies in this beautiful, hidden pattern called self-similarity. This right here is the defining characteristic of fractals. It's the engine that creates all this mind-boggling complexity. Self-similarity is exactly what it sounds like. It's when you can zoom in on any tiny piece of a shape, and that little piece looks pretty much the same as the whole thing. Think of a fern frond. Each little leaf looks like a miniature version of the entire frond. This pattern just repeats, over and over and over, building infinite detail out of one simple recurring rule. Now, this idea comes in a couple of different flavors. On one hand, you've got exact self-similarity. This is the perfect, pristine mathematical kind you see in things like the Koch snowflake. Every zoomed-in piece is a perfect, identical copy. But then there's statistical self-similarity. That's what we see in nature. A small piece of a coastline isn't an exact copy of the whole thing, but it has the same character, the same general level of jaggedness. And that consistent roughness is precisely why the length just keeps on growing.
Okay, so if we've got these weird, infinitely complex shapes, how in the world do we measure them? It turns out we need a totally new kind of ruler, one that can handle dimensions that aren't just simple whole numbers like 1, 2, or 3.
Really think about that for a second. That wiggly coastline is obviously way more complex than a simple one-dimensional straight line. But it doesn't actually fill up a whole 2-dimensional area, does it? It just kind of exists in this weird in-between space. So how do you put a number on that?
The answer is something called the Hausdorff dimension. Now, that sounds complicated, but you can just think of it as a roughness rating. Instead of being a whole number, it's a fraction, a decimal, that tells you exactly how wiggly, how crinkly, how much a shape is trying to fill up space.
And here's what that looks like in practice. A simple line has a dimension of exactly 1. No surprise there. A flat square that fills a plane has a dimension of exactly 2. But look at the Koch snowflake, that classic fractal. Its dimension is about 1.262. That number, that decimal, is the mathematical proof. It's telling us, loud and clear, this thing is fundamentally more complex than a line, but it's still not quite a 2D plane. It's something else entirely.
So let's actually take a closer look at that Koch snowflake. It's probably the poster child for just how strange and wonderfully contradictory these fractal shapes can be. The way you build it is so simple. Seriously, you could do this on a napkin. You just take a line, you split it into thirds, you pop out the middle section, and you replace it with the other 2 sides of a triangle. That's it. Then you just do that again to all the new lines, and you just keep going. And here's the magic trick.
With every single step, you're replacing one piece of the line with 4 smaller pieces. This means that every stage, the total length gets multiplied by 4/3. And since 4/3 is bigger than 1, well, the length just never stops growing.
And if you repeat that simple process an infinite number of times, it leads you to a completely mind-bending conclusion. The boundary of this shape, its perimeter, is literally infinitely long. And this is where your brain might start to melt a little. Even while you're drawing that infinitely long line, the area that it's enclosing remains perfectly, completely finite. It never grows out of control. In fact, it adds up to exactly 1.6 times the area of the first triangle you started with. You get an infinite boundary wrapped around a totally finite space. Wild.
So, this core idea that super simple rules can generate infinite complexity is our bridge to what might be the most famous and recognizable image in all of mathematics, the Mandelbrot set. This thing isn't just a pretty picture. It is the visual language of chaos theory. And what's so incredible, so mind-blowing, is that all of this unbelievable, psychedelic, endless universe of detail, comes from repeatedly crunching the numbers on that one tiny little formula. That's it. You just check if a starting number stays stable or flies off to infinity when you run it through the formula over and over. It's the ultimate example of profound, spectacular complexity emerging from the absolute simplest of rules. That intricate, fuzzy edge of the Mandelbrot set isn't just for show, it's a map. It's literally the border, the frontier between systems that are stable and predictable and systems that spiral into total, unpredictable chaos. Fractals are the geometry of that tipping point.
And I promise you, this is not just some abstract mathematical curiosity. It turns out, nature and technology have been using these tricks all along. Fractal antennas in your phone pack a huge effective length into a tiny chip. Image compression algorithms look for self-similar patterns to save space. And our own bodies, our lungs, our blood vessels, they use fractal branching to cram an enormous amount of surface area into the very finite volume of our bodies. It's just geometry as a tool for maximum efficiency.
So yeah, we started with what seemed like a silly question about a coastline, and we ended up at the fundamental geometry that describes the boundary between order and chaos, the structure of our own bodies, and the tech we use every day. Fractals, it turns out, are the language that our complex, messy reality is written in.
And that kind of leaves us with one last big thought to chew on. If the line that separates simple, predictable systems from chaotic, unpredictable ones is itself infinitely complex and beautiful, what does that tell us about our universe? What other simple, repeating rules might just be hiding in plain sight, generating the incredible, intricate reality we see all around us?